In our previous chapter, we talked about error and how all measurements have error and ways to do calculations involving error. In this chapter, we're going to have a brief introduction to statistics. If you want more of this, of course, you can take an actual statistics class. But the idea of this chapter is to give you enough information about statistics to be able to assess error and to answer how well we know a value when we've done a certain number of measurements doing quantitative analyses. So the first place we're going to start is the idea of a normal or Gaussian distribution. And this is essentially a way to think about random error. So this doesn't apply so much to systematic error, but this is more random error. If we do a measurement over and over again, there will be some amount of random error in it. And some values will be higher, some will be lower, but you'll have some average value that these measurements are clustered around. So say, for example, we have light bulbs. And we want to know how long do our light bulbs last. So we can measure a bunch of light bulbs, say we're a light bulb company, and we turn them on and keep them on constantly until they die. And we do this for, a few thousand light bulbs just to get an idea of how long these last. Maybe one will last for 55 hours. Maybe another one will last for 57 hours. Maybe you have an extra special one that lasts for 65 hours. Right, but we'll get a bunch of different results. And we repeat this a bunch of times. And if we plotted all these light bulb lifetimes, as a histogram, right? So our x-axis is the number of hours, and the y-axis is how many bulbs survive that long. We can get a plot that looks something like a figure from your textbook. So we'll pull this up. So this is figure 4.1, and this is a bar graph and a fitted Gaussian curve that describes the lifetime of a hypothetical set of light bulbs. So, these are several hundred hours in comparison to the 50-something hours I was putting down. But you can see there'll be some average value, in this case 845.2. So this X bar that represents the mean. The average value is 845. We have some that last significantly less than that, some that last only 500 or 600 hours. Whereas we have some that last a lot longer or over 1,000 hours, but the average is here. And we can describe this with a mathematical function, right? The actual data is this noisy spread, right? This histogram, this distribution of different lifetimes. We can fit this with a mathematical function that's called a Gaussian function and get some information about it. The two main things that we're interested in about a Gaussian function are the mean, so what's the average value, and then this S, the standard deviation. How far on average is any particular value from that mean value? So let me go back to my whiteboard so I can write. All right, so this is our Gaussian function here. Now, so the properties that we care about are the mean, x bar, which is just we add up, mathematically write this as we add up all the individual x values. So x sub I here would represent each individual point. So these would be all our different lifetimes. And then we divide by the total number of measurements. And this is just how you already know how to take an average. This is how you do it. Now the other, just to define these, x sub I is each individual measurement and n is the total number of measurements. Now the other thing we're interested in is how wide is this curve? So, and that is related to the standard deviation that we define as S. So S is equal to the square root of the sum of all of the differences. So the difference between each individual measurement and the mean value squared divided by the total number of measurements minus 1. And so this measures how closely individual measurements cluster about the mean. Okay, so if the standard deviation is small, what that means in terms of what our Gaussian curve will look like, a small s would mean a very narrow distribution, meaning our curve is very narrow. And most of the values are fairly close to x bar. A large s, on the other hand, means a very wide curve like this, and each individual measurement, we pick one value of x sub I here, may be pretty far from our average value. So there's a big spread, big range of possibilities that we get from our measurements here.